Okay. In our last video, we talked about we talked about kinetic energy first. That was pretty straightforward. Then we talked about gravitational potential energy, and we saw that the equation for gravitational potential energy was m times g times h, mass times acceleration due to gravity times the height of the object. Now, because we're talking about height, in general, we assume that gravitational potential energy is going to be zero if the object has a height of zero. In other words, if the object is on Earth's surface or the floor. And this can get a little tricky sometimes, because if we're in this classroom that I'm in right now, you might say, okay, well, where's the gravitational, where is the height zero? You might say, okay, on the floor. Well, imagine someone standing outside next to the building. They would look at our floor and say, no, that floor is 3 or 4 meters up in the air. The floor, or the ground, is really where they're standing. But then you could also say someone else, in Sequoia, we're at an elevation of about 1,000 feet above sea level. What if you had someone go over to sea level, out to the ocean, and say, no, this is where the height is zero? It turns out that where the height is zero doesn't matter all that much as long as you're consistent about it, so it's fine to say that the floor is where there is zero gravitational potential energy. It doesn't end up mattering all that much. It's something we'll deal with more in AP Physics. All right, so our main example for gravitational potential energy is going to be a case of, well, what's easier? Is it going to be easier trying to pick something straight up or using a ramp to push or pull it up? You might see if you're ever helping someone move, or if you're just trying to get something maybe up to like a second story. It's very difficult to lift heavy objects straight up, so sometimes we use ramps. So let's say that we have a moving company trying to move a heavy object from the ground to the second story of a building. The object's got a mass of 50 kilograms. What is the initial gravitational potential energy of the object? Okay, well, that's pretty easy. If we're looking for gravitational potential energy, that's PEG. It says initial, so I'm going to put a little I there just to remind myself. And that's equal to the mass times the acceleration due to gravity times the initial height of the object. Well, we know that the mass is 50 kilograms. We know that the acceleration due to gravity is 9.81 meters per second squared. And the initial height of the object is 0 meters. It's on the ground. Okay, it's on the ground, so the initial height is 0 meters. So the initial gravitational potential energy has to be 0 joules. Now, in order to lift the object straight up to a height of 4 meters at a constant velocity, how much work must be done? Well, let's think about what force would be doing the work. It would be the applied force. So we need to know the work done by the applied force equals the applied force times the displacement times cosine of theta. I don't know what the applied force is because it doesn't tell us. That means I should draw a free body diagram. Here's our object, axis, very simple free body diagram, Fg down, applied force up. F net y equals Fa minus Fg equals may. Let's assume that it says we're lifting at a constant velocity, so there's no acceleration. So the applied force is equal to mg, because that's what Fg is equal to. So the work done by the applied force equals mg d times cosine of theta. Notice that since we're lifting the object up, the applied force and the displacement are in the same direction. Cosine of theta is going to end up being 1. The work done by the applied force is 50 kilograms times 9.81 meters per second squared times the displacement of 4 meters upwards. Now notice that mgd sounds an awful lot like mgh, okay? Matter of fact, it is the same thing. We're lifting something up, therefore the displacement is just how much height it's gained. So the work done by the applied force is 50 times 9.81 times 4, 1,962 joules. That's how much work is done by the applied force. What's the new gravitational potential energy at this height? So the final gravitational potential energy, look at this. It's the same exact calculation. 50 kilograms times 9.81 meters per second squared times a final height of 4 meters off the ground. 50 times 9.81 times 4. All of that work that was done went into changing the gravitational potential energy of the object. So the object initially started with 0 joules of gravitational potential energy. The applied force did 1,962 joules of work, transferring that energy, and all that energy ended up as gravitational potential energy. Now, why would we use a ramp? Suppose instead that the company decides to pull the object at constant velocity up a frictionless ramp that is 10 meters long and reaches that same height of 4 meters. So here's what a picture of that ramp would look like. The ramp itself is 10 meters long, and its height at the top is 4 meters. What is the angle between the ramp and the ground? That's this angle right here. I can solve that using trig very easily. Okay, I can solve that using trig. You learned this trig back in like middle school. You learned SOHCAHTOA, and what that means is it's just a mnemonic device to help you remember the ratios for calculating sine, cosine, and tangent. So sine is equal to the opposite side over the sine of the angle is the opposite side over the hypotenuse. Cosine of an angle is equal to the adjacent side over the hypotenuse. And TOA, tangent of an angle, is the opposite side over the adjacent side. We're not given the adjacent side. We are simply given the opposite side of the triangle, 4, and the hypotenuse of 10. I can figure out this angle by taking the sine of theta equals opposite over adjacent. And I can say that the sine of theta equals 4 over 10. 4 over 10 is 0.4. Now I have to take the inverse sine of both sides. The inverse sine is what will allow me to figure out what theta is. I can't just do the sine of 0.4. I need to take the inverse sine of 0.4. So theta equals inverse sine of 0.4. That's the extra button on your calculator, okay? Inverse sine, you gotta hit second and then sine. So 0.4 second sine, and I get an angle of 23.58 degrees. That's the angle that the ramp makes. So what sine is on your calculator, it's really just a function button on your calculator that helps you to determine what the angle is given some side lengths of a right triangle. That's all sine tells you. All right, how much work must be done in order to pull the object up the ramp? All right, so we know the angle of the ramp now. That's great. How much work must be done in order to pull the object up the ramp? So again, we're kind of looking for the work done by the applied force. But in this case, I'm not told how much force that is. I know the displacement. I know to get up the total ramp, it's got to go 10 meters. And the angle here, well, I suppose the applied force and the displacement, the applied force is going to go up the ramp, the displacement is going to be up the ramp. I guess those are in the same direction, so I can cross this off. Since cosine of 0 is 1, you can write that this is 1. The issue is I need to know what the applied force is. I don't know what it is. I need to draw a free body diagram. This is a nice little review of ramps, by the way. So I'm given the, let's see, object. My axis is going to look like this. X, Y. The force of gravity is going to go straight down. The normal force is perpendicular to the ramp surface, so that's in the positive Y direction. It's a frictionless ramp, so there's no friction. The applied force is directed up the ramp, like so. FA. Fn is in the positive Y direction, Fa is in the positive X direction, Fg is in neither of those directions. We need to split that into components. We know that theta will appear between Fg and the component that's perpendicular, that's right here. Therefore, since this is the component that is perpendicular to the ramp surface, it's also the component that is adjacent, where the angle is. This component is going to be Fg cosine theta. Make this look a little clearer. This component over here is Fg sine theta. In order to find the work done, I got to do the net force equations, or in order to find what the applied force is, F net x equals Fa minus Fg sine theta equals max. Let's assume we're trying to pull the object up at a constant velocity, like it says. So this acceleration is 0. The applied force is equal to mg sine theta. That's going to be useful over here. But before I get to that, let's just do the net force in the x direction, or in the y direction as well. We have Fn minus Fg cosine theta equals may. The object is not accelerating up off of the ramp surface or down into the ramp surface, therefore the acceleration in that direction is 0. The normal force must be equal to mg cosine of theta. If I went really fast for you through that ramp section, you can always just go back and take a look at the sections on ramps in the videos that we've done so far. Anyways, I now know what the applied force is. It's equal to mg sine theta in this case. So I'm going to plug that in. mg sine theta d. The work done by the applied force is equal to, let's see, the mass of the object is 50 kilograms. The work done, or excuse me, the acceleration due to gravity is 9.81 meters per second squared. The sine of theta, remember theta is the ramp angle. We just figured that out as 23.58 degrees. So sine of 23.58 times d, the displacement of 10 meters. We calculate for the work done by the applied force. Let's see. Let's do the sine first. 23.58. Take the sine of that times 10 times 9.81 times 50. Look at that. Within rounding error, we get an applied work done by the applied force of 1,962 joules again. That looks familiar. That's the same amount of work that it took to lift something straight up. So wait, if the work is the same, what's the